So up to this point, we have done, with the central limit theorem, we learned about the means. Put your phone away, please. We learned about means, and we learned formulas and the conditions that deal with means. And we're going to focus on the next week or two on proportions. And these are the conditions for the proportion side. We have formulas that we can use, notation, etc. And so this is all stuff we already know. Would you agree? We know this. We've been working with it for a while now. And please do not write all this down, okay? I'm going to tell you what's important, but not all of this is important, or for you to write down anyway. What you read about in chapter 18, and hopefully by reading and taking notes, you felt it a little bit more productive than just doing the just checking and copying the answers at the end of the chapter, because that's what most of you do, and I understand that. So we're going to change that up a little bit, because I really want you to be able to read and understand what it's talking about. The first few pages I asked you to really kind of pay close attention to, and I talked about interpreting confidence intervals. And I think the example the book used was like the Red Sea fans, right, and whether or not they were diseased or not. And they asked you, like, how would I be able to interpret? What is it okay to say? That kind of thing. So I'm kind of giving you a couple of examples of some contextual, how to interpret an interval. So when you're talking about a confidence interval, let's kind of take a step back for a minute and maybe define what a confidence interval is. This is the interpretation of one, but what is a confidence interval? What are we hoping to do with it? We'll talk about how to create it in a few minutes, but what's the point of a confidence interval? Well, we're hoping to capture something, okay? What are we hoping to capture? What do we want to do? What's the purpose of it?
Aren't you trying to find the actual probability?
Yeah, I think that's kind of what you were trying to say, right? So in terms of the CFAN problem, okay, is it possible to find the real parameter, the real population proportion of diseased red sea fans in the oceans? No, not possible. There's no way for us to make sure that we've picked every one, we've checked every one, etc. So what we're hoping to do is collect samples. And those samples, we can create what's called a confidence interval, and we're hoping to capture the real proportion. So really what we're doing is using samples to say some things about the population, okay? So here's an example of something in context that talks about favoring a candidate, okay? And here's an interpretation. We are 95% confident. Let's stop there. What the heck do they mean by 95% confident? What does that percentage mean? It's 95% chance that what? Careful with that. There's a 95% probability of something. There's a 95% chance that we will capture the population parameter. There's a 95% chance of that the true population parameter that of people who favor is between that. Okay, that's a way to say it. Okay. So it has to do with how confident we are, how sure we are that the interval we create really is going to capture what we're looking to capture. Okay? Here's another one underneath. Okay? You don't have to write them down. They just happen to be in words. Okay? In this first example, what's 95% called? It's just, just in general terms. It's called the confidence level. .51 to .53 are just really the endpoints of the interval. Wouldn't you agree? Okay, so I'm just going to write that. In the second example, we can use this. How is 42 to 54% the same thing as that? 48 plus or minus 6. Matthew? Right. So 48 is the middle, and if I add 6, I get 54, and if I subtract 6, I get 42. They both describe the same thing. They are equal, okay? There is another way to write it. The other way to write it would be this, 42.42 to 0.54, and actually write it like that. All three of those mean the same thing. Okay, they're just different notations. AP tends to like the one that's here, 48 plus or minus 6. The 6% has a name. Do you know what it was called? Begins with an M. Margin of error. Okay? And margin of error is what you are actually adding or subtracting from your statistic, okay? From the middle, as we said it that way. You ever like when we're, anyone watch any of the outcomes of any of the primaries where you're like on the news and you're watching them come in? They always have that little saying at the bottom, plus or margin of error plus or minus 3%. That's what they're talking about here. That's where this is coming from, okay? Now, we're going to take for a little bit, we're going to talk about the confidence levels. And there's three that are widely accepted that we use all the time. And those are 90, 95, and 99%. Okay? If it doesn't specify what the confidence level is, or what the confidence level is, we assume 95%. Okay, that's kind of like the safe background, or the safe fallback, I should say. But otherwise, it would specify specifically. And we're going to talk about why those are important in creating the confidence interval, because they are very important. They make a big difference. Here is the CFAN example. Okay, I want you to read it to yourself, for example. Or read it to yourself, for example. Read it to yourself for a minute, and see if you can't answer what the sample proportion is, what's p hat, and what is the parameter p. When I read this, I see three numbers. Well, 2000, I guess, is the date, though. I've got this, and this. Only two of those numbers are important. Which number doesn't really play into either of these? The 40 feet, okay? That it doesn't really play into this. Okay, extra information. The 54 and the 104 are very important, though. Okay? Which one is p hat? Got to write it as a fraction. Remember, p hat is a proportion, right? So it's either written as a fraction, a percent, or a decimal. The total number of CFANs that I tested was 104. 54 of those had the disease. So we write it as that's our sample proportion. What's the parameter? What's the actual number of CFANs in the ocean that have the disease? Your guess is as good as mine. There's no way for us to know that, right? That's what we're hoping to capture. Would you agree? But it's not going to be stated. So we're hoping to capture it in our interval that we're going to create. Okay? Now, when you guys did some reading, what is standard error versus standard deviation? Because they talked about that. What's the difference? The formulas look very similar. The only difference I see is these silly little hats. Would you agree? What's the difference? Cameron? Okay. The standard error estimates the standard deviation. Remember, the standard deviation formula was the square root of PQ over N. Do you agree? That's what the standard deviation of the sampling proportions is. But I don't know P. You just told me. I have no idea what it is, right? There's no way for me to know that. So if I can't figure out what P is, the best thing we can do is to estimate it with P hat. Okay? That's really the only difference. So if we're using the sample proportion for our standard, it's called the standard error. And it's no longer called the standard deviation. But it acts the same. Okay? It's a good estimate. All right, so read these four things to me, or to yourselves, and tell me which of these four things can we say 100% is true. What can we say about the CFANs? So read them all, and then you tell me. Can't say that. We can't say number one. We have no idea. The 51.9% might be my p hat, but it's not something that we can say that's definitely true. How about number 2? What do you think, Angelica? Can't say that either. I mean, it might be true, but we can't say it's probably true. We just don't know. How about number 3, Karen? We don't know anything. We're pretty confident that it could be, okay? We created a confidence interval, but we don't know that, okay? What do you think about number 4? Yes, that is actually what we can say. And that's all we can say, is that we're 95% confident or 95% sure that the true proportion of C-fans is in this interval. I'm a very visual person, and I needed to create something to help me see what it is we're trying to do with this whole confidence interval thing. Let's say that this line right here is the parameter. It's the true population proportion. Okay? And let's say that each of these little black lines represents a different confidence interval. Every time we take one sample, we can create a confidence interval with just that one sample. I put them back. I take another sample, create another confidence interval, put it back. Take another sample, create a confidence interval, put it back. And so I've taken and I've created all these different confidence intervals. Notice, most of the time, the red line is in there. Most of the time, we've captured the parameter. Every once in a while, and this is not, I would have to have 90, a lot more to show it, but if I was 95%, 95% of them would capture them, and 5% wouldn't. Question? One sample, yes. That's a good question. Okay? But each sample is a little bit different. So the confidence interval is going to be a little bit different. And most of the time, it's going to capture it. And actually, we have a percent of time that it should capture it. Okay? That's just for me. It's a visual for me. All right. So let's talk about how to create the confidence interval. If you would get your formula sheet out for me, on the very top right-hand column on the formula sheet, I want you to look at it and tell me, what does it say for the confidence interval? Because it doesn't say any of this stuff. It says something. What does it say? Look at your formula sheet. I think it's the second thing from the top. It says statistic, statistic, plus or minus critical value times the standard deviation of the critical value. It probably says that. Oh, of the statistic. Okay, that's fine. What? Right, that's all words. This is a generic confidence interval formula because we're going to do confidence intervals for one proportion, two proportions, one mean, two means, t-distributions. We're going to do a lot of different confidence intervals. This one formula applies to them all. When we talk about a statistic with what we're doing right now, isn't that a proportion? 54 out of 104 C-fans had the disease. So this is p hat. This is the statistic. The critical value for now, and it will change when we do t-distributions, and we could have a different kind of, there's other critical values. But right now, the only kind of distribution we're going to be working with is normal distributions. Because we know that we can approximately normal as long as NP is greater than 10 and NQ is greater than 10. Would you agree? As long as those conditions are met, it's normal. So we're going to be looking at Z values. Okay? Z values go with normal distributions. Z star is the notation for the critical Z value. Okay? This is your critical value. We're going to talk about how to find that critical value in a minute. And I'm actually going to change this. I'm going to call this the standard error. Because we really aren't given a standard deviation. Isn't that just the square root of P hat Q hat over N? Okay? So yes, this is true. And if you notice, or if you remember, this whole part of the plus or minus, by the way, on the right-hand side of that, after the plus or minus, what's that called again? begins with an M, the margin of error. Whatever you add or subtract to either side of the statistic is going to be the margin of error. Okay? So, the statistic and the standard error we can find. 54 out of 104 CFANs. We can figure it out. We're going to figure it out in a minute. But before we get to that part, I really want to focus on the on the Z, the critical Z value. How do I find that? Remember how I said that there is 3 very common percent of confidences? And that actually the Z star that goes with each of those is the same every time. So if you know you're 95% confident, you can put in a 1.96 for Z star. If you know that you're 99% confident, you can put a 2.576 in for Z star. So I'm going to show you how you can find it, okay? Because what if you don't memorize those numbers? How do I find them? So I'm going to start by showing you the 95%. How did I come up with this number? You ready? When I'm talking about a confidence interval, the 95% confidence is the middle 95%. Okay? That leaves what in each of the tails of the normal distribution? Together it would be 5, so each tail would be 2.5%. If I'm looking for this Z star value, and by the way, over here would just be the negative of it, okay? One would be negative, one would be positive. We're always worried about the positive version, okay? I have to figure out, first of all, what function am I using? Am I using normal CDF or inverse norm? If I'm given the percent and I want to find the value, I use inverse norm, okay? So I'm going to say inverse norm. But I'm not going to put 95% in. Why not? I'm not going to put 0.95 in. Because I still have a tail down here to add to it. So I have to put both of them in. So what would that be? 0.975? Would you agree? 95 and 2.5 together? Just one of the tails. So 0.975 is what I'm going to plug in. So it's the middle plus one of the tails. If it's a Z value, what's the mean and standard deviation that I'm looking for, or that I'm dealing with? Always, for any Z star or Z value. The mean would be 0, the standard deviation would be 1. Plug it into your calculator. I want you to actually try it. Get your calculator for me, James. Did you get 1.96? Okay, good. So what's going to change if I'm looking at 90%? I want you to find the critical Z value for 90% confidence. What's going to change? Hang on, Byron, what's this talking? Yeah, so the middle's going to change, right? And the tail's, so the area's going to change. We're still going to use inverse norm. But if we do this and we have 90% in the middle, what does that leave on either tail? 0.05, right? So I'm looking for this Z star value, so it's going to be inverse norm what? 0.95, because it's the middle 90% and one of the tails. Again, we're looking at 0 and 1. You should get this. Double check me. And that's really where I want you to round it, 1.645, okay? Now I show you the process here because on a future quiz or test, I might ask you to find the critical Z value that goes with a strange one, like 92% confidence or 87% confidence. And I want you to be able to come up with the Z star that goes with it, okay? I've seen that on released AP exams before. Yes, ma'am. The center plus one of the tails. That's all it is. It's not hard, right? It's a matter of knowing how to do it. Yes. You could do, if you did inverse norm 0.025, you would just get the negative Z star. But we always want to do it with the positives. Okay? Yes. You take 1 minus this and divide by 2. Because there's 2 of them. Any other questions? I am okay with if you just want to memorize these numbers. You're not going to have to show me every time how you found the z star. I will tell you on the next quiz you will have to do a weird one, or the next test, okay? But these 3 will most often be used, okay? It's good. It's probably a good idea to memorize them so you don't have to find them every time. All right, good. So let's jump into it. Let's actually let's do a problem. So read this to yourself. I want us to come up with p hat, q hat, n, and z star. Because those are the things that are in the formula. So give me one of the 4. Lexi, give me one of the 4. What do I know? What is it? That's exactly right. I agree. Perfect. In our survey of 1,013 people, we found 537 of them believe that affirmative action program should be continued. I agree. Give me another number up here that we absolutely know. Ricardo, what do you think? Okay, somebody else. Byron? Z star. Yes. And that's because of, we're told it's 95% confidence. So I know that the critical z value that's associated with 95% confidence is 1.96. I agree. Give me something else I know. Okay, I know n is 1,013. I notice y'all are avoiding q hat. Not negative. It's still over 1,013, but what's the numerator? Where'd you get that? I agree, it is 476. Yeah, these together should add up to be 1,013, right? So if I know 537 of them said they should be continued, shouldn't 476 of them say they shouldn't be continued? So it's just a complement of that. Okay, good. So we're going to use these numbers and we're going to plug them into our formula. The confidence interval formula is p hat plus z star times the standard error formula. So I'm just going to plug in my numbers. Okay? So p hat, 537 over 1,013 plus or minus 1.96 times the square root of 537 over 1013 and 476 over 1013. I'm going to pause the recording for a minute, and I want you to try this on your calculator and tell me what the interval is. Let me know if this is what you got. I try to do it one step at a time. I found the standard error first. Yes, dear. 0.5301 minus 0.0307. Remember, you have to take your statistic and add and get the upper bound and subtract and get the lower bound. Okay, good. Any questions on where these numbers came from? Boris, I see some confusion. Second to last step, this one here, I just multiplied these two together to get this number. Cameron. I just multiplied 1.96 times 0.01. The last one? Okay, so in order to get the 0.561, I added them together. In order to get the lower bound, I subtracted them. Because you have to add and subtract, right? This number here it should be in the middle. It's the middle of the interval. And then you can add and you can subtract to get the upper levels, or the boundaries. Okay? Anytime you create a confidence interval, I also want you to write in context what the heck you're saying. So we're always going to start the same way. Okay? We are 90, in this case 95%. It could change. That could be a different percentage, but in this case it was 95%. So we're 95% confident that the true proportion of. You're always going to start the same way. Now we're going to put our context in it. Okay? What's the context here? Is the affirmative action, right? Who believes that those programs should continue? So we are 95% confident that the true proportion of people who want affirmative action programs to continue is between 49.9% and 56.1%. And that's really all we can say. We can't say that 50% it is. We can't say we know it's 56%. We can't say any of that. All we can say is we're pretty darn confident that between those two values is what the parameter suggests. I'm okay if you leave it with the decimals, okay? But since it's context, usually we do it in percent with context, okay? But I'm not going to be super picky about it. How do we feel? Oh, yes. In a minute. Okay. So we feel okay? What did we do? All we did was take a sample. We sampled 1,013 people. We got some answers. And then we created this interval. If I picked a different sample, would my interval be exactly the same? No. But I bet that no matter what we did, as long as the conditions were met and whatnot, wouldn't we be able to capture that? I mean, it might be a little bit higher, it might be a little bit lower, but we're pretty confident it's going to capture it. Okay? What if we were satisfied with only being 90% confident? The Z star changes, and that's the only thing that's going to change. So where are we here? So 0.5301 and 0.05, remember that number, 0.5301, 0.01568. So 0.531, and what was this one, 0.01568? Told you all to remember, 68. The only thing that changes is my critical Z value, that Z star value. If it's 90%, what number goes in there? .645. Good. So go ahead and do the math. Tell me what that interval is. Okay? Is this interval wider or more narrow than the one we did before? It's more narrow. Why does that make sense? We're less confident, right? We're not as confident now. We're only 90% confident. But my interval's smaller. The more confident we get, guess what happens to that interval? It gets wider. The more confident, because we want to capture it, right? That's what we're trying to do. So the more confident we are, the wider it's going to be. The less confident we are, the more narrow it's going to be. What happens, what do you predict is going to happen with 99%? It's going to be super big, little tiny, bigger than before. Do you have a question, sweetheart? Is it not 0.531? It's 0.5301. Is that the problem? All right. Thank you. Oops. Is that why it changes then? Okay. Thank you. So is it so tell me what it is based on that. Okay, thank you. That was my error. I appreciate it. All right, 99% confidence, what do we expect to happen? Wider, okay? And again, the thing that changes is just your Z star. The standard error doesn't change. The proportion that believe isn't going to change. What's the Z star that goes with 99%? 2.576. So let's figure out what this interval looks like. It is wider, isn't it? We expected it to be wider because we're more confident that we're going to capture it. So it should be a lot wider. Okay, good. You guys ready for a Valentine's Day treat? Yay, let's do it. All right, so I went to 3 different stores last night to find you conversation hearts, okay? Because, you know, you're a cutie pie and LOL and whatever they say on them. So I'm going to walk around. Our goal here is to figure out or to create a confidence interval of the proportion of pink candy hearts that are in our sample, okay? So what I want you to do is put your hands out in the cup. I don't want them to fall out everywhere. And I want you to count the total number of hearts I give you and then the number of just pink ones, okay? We're going to treat our entire class as one sample, okay? So what do we need to find? We need to find the total number of what? Pink ones, and the total number of all of them. So we need to find our sample size, our N, and then we need to create our P hat. So what I'm going to do is I'm going to ask you first how many total you have, and we're just going to add them together on the calculator. And then I'm going to ask you how many pink ones you have, and we'll add them on the calculator. We'll come up with our values. I'm going to pause the recording for this because y'all don't need to hear this. All right, so out of our 450 candy hearts, 32 of them were pink. Okay, so let's write that information down. 450 total, and 32 are pink. Yeah, I don't know if you guys heard, but all activities, afternoon activities are canceled tonight. Basketball games are canceled tonight. They're expecting snow. I'm supposed to be driving to Maryland. Yes, from 6 to 10. So what information can I create from this? P hat. I absolutely can do P hat. What is P hat? P hat is 32 divided by 450. Perfect. Can I also come up with Q hat? Sure. Where'd the 418 come from again? Because you're just trying to find the complement. 450 minus 32. The two numerators together should total the denominator. Okay? What other information can I come up with? Can I help you?
I get my coat from under this.
Go. What other information can I get? N. What's associated, what comes with N? Huh? What is it? Oh, the total, yes, 450. And then what else can I come up with? Z star. The critical Z value is associated with, yep, it's associated with the 95%, so it's 1.96. I have all the information I need to create a confidence interval. Based on our sample, we can say we're going to be 95% confident that the real proportion of pink sweethearts, conversation hearts, is going to be between these two values. So let's do that. You guys go ahead. So there is a shortcut, obviously. I'll show you what that is in a minute. But for the long cut, let's make sure we know what we're doing. So it's 32 over 450 plus or minus 1.96 times 32 over 450. And then we have 418 over 450 all over 450. So that's kind of the long version. Okay? And then I got that interval. Did you guys get that as well? What's the margin of error? Did you guys get that? Yes? No? You should have. I don't know what 32 divided by 450 is. Oh, no, I'm sorry. That's the middle. Sorry. Is that correct? That's right. That was the left-hand side. Okay. Sorry about that. And then the right-hand side. Did you get 0.0237? Good enough, rounding wise, okay? you come up with this answer. Now, there is a shortcut. Would you like me to show it to you? Please. The reason I make you do it the long way first is because it really is important, and I have seen AP ask you to write out the whole formula. I've seen it written just like this, where you have plus or minus the margin of error, and then you can just find the interval itself. So how do I do that using the shorthand? So everybody should have a calculator, because it's all in the calculator, and I'm going to show you how to do it. Okay? We're going to be spending quite a bit of time in this particular functionality of the calculator. We did a lot with stat calc. Do you agree? I'm sorry, yeah, 1-bar stats. We've done a lot there. If you keep arrowing over to the word tests, this is the beginning of inference. Okay? And inference is all of these hypotheses tests. Well, there's also intervals in here. If you keep scrolling down, and by the way, at the end of the course, you'll know what almost all of these tests mean and how to use them. Exciting. There's a lot. We're worried about one proportion z interval. That's all we have. We have one proportion. Do you agree? It was 32 out of 450. That's our sample proportion. That's what we came up with. So that's the test we're interested in right now. Option A. If you hit enter, it's going to ask you some questions. The good news is if you pick the wrong test, you'll know because you won't be able to answer the questions. Okay? Because it's giving you some prompts. What do you want me to do with this? What's x? It's the number of pink hearts we had. How many do we have? We had 32. The n was what? 450. The confidence level is 95%. We hit enter. Did we get that? Huh? You didn't get that? Try again. 0.04737.09486. Isn't that what we got? That's how I got it so quickly. Okay? It's not cheating. It's using the technology that's available to you. Then you would know how to do it the longhand, because I've showed you both. Yes? Yeah, one proportion z interval. Yeah. That's what I got. Okay? Good? Yeah. Not bad, right? Here's another question I have for you. What if we were given the interval, just the interval? Could you find the margin of error? Let's say that I was given this interval. What was it? Come on. What was the interval? Just smartboard just died. That's the problem. So 0.0473. Let's just scroll up. Let's do it that way. I'm given this interval. Okay? I want to be able to find the margin of error. How would I do it? First of all, I probably want to start with the middle. How do I find the middle of an interval? If I'm given two endpoints, how do I find the middle? You're eventually going to divide by 2, but what do I have to do first? Add them together and divide by 2. Do that for me. Add these two numbers together and divide by 2. Find the middle. What number is that? That's p hat. It's where I start. Now I'm going to add and I'm going to subtract on either side of that to get the endpoints, right? What number I add and subtract is the margin of error. So how do I find the margin of error? You don't throw things. I take my middle, 0.0711, and I'm going to add some number, and I'm going to get this. Would you agree? So I take my upper endpoint and subtract the middle, and that gives me my margin of error. I could go the other way, too, if I wanted. So 0.0946, oh, sorry, 486, minus my p hat, my margin of error is 0.02376. It's the margin of error I got. Okay? So I can be given the interval. I can use my calculator if I want, find the interval, easy as peasy, and then I can find the margin of error if I need to. Okay? No big thing. Here's a question I have for you, though. We really think that this sweetheart candy is a bunch of liars. Okay? I think that there's really a lot more pink candy hearts than our sample leads is telling us. The manufacturer claims that 10% of hearts are pink. Do we believe them? Why don't you believe them? Because they're punks. I'm looking for statistical evidence. What statistical evidence do we have to either support it or not support it? The interval is the evidence. So let's write the interval down one more time. I can never remember it. 0.04737. And then what's the upper one? 0.4826. Six. 10%. That's their claim. If I was to interpret this interval, what would the interval say in words? We are 95% confident that the true proportion of pink hearts is between 4.7% and 9.5%. Where's 10? Not in there. Hi. Hang on, I'm recording. I feel like this is going to be serious. Excuse me. What?
I was afraid that someone, Corinne, had like an emergency and she had to leave, so she can't stay.
Yeah, she emailed me.
Oh. She told me that she couldn't.
Anyway. Huh? What? Sorry about that. Okay, anyway, what is happening here? In the contextual situation, between 4.7% and 9.5%, we're 95% confident that the true proportion's there. Where's 10? Not in that interval, right? That's our evidence. Well, we're 95% confident that that is it. So it's in there. Our next interval might be lower. It might be higher, right? But it might be lower. Because our interval did not capture the claim, we have evidence to suggest that they're a bunch of liars. Okay? Huh? Can we sue them? Okay? Because 10% is not, and that's what you actually have to physically write this, okay? I want this sentence written. Because 10% is not captured in the interval, comma, the manufacturer's claim is invalid, false. Liar, liar, pants on fire. All right? How do we feel about this? Did it help that you read it first?
We did.
Right, and you took some notes first? I think maybe sometimes it's a better idea. That's the goal. When I assign you to read the chapter, it's not because I'm trying to torture you, okay? It's because I really want you to understand when you come to class what we're talking about, all right? So next time I assign read the chapter, I might still assign, I might give you notes again, but really try to understand what they're saying. I think it will make for a better experience for when you come into class, okay? So I do have homework. Let me go ahead and give it to you. I'm going to text it to you as well. But it's in chapter 18, which starts on page 489, but only the first problem's on page 489. You only have 6 problems to do, but each of them have several parts, as you can imagine. Okay? Oh, get over yourself. It's not that much. Okay? All right.